path planning and trajectory tracking are two of the fundamental tasks when it comes to mobile robots. Those tasks can be studied in a two-step approach. Step 1. Plan a path from a start position to a goal position. Step 2. Track the previously created path. Both tasks can be tackled at once by using implicit curve navigation techniques. Paths are planned using implicit functions, whilst trajectory tracking can be achieved by using artificial vector fields. In order to control our vehicle's navigation towards the curve generated by the implicit function, we used a fuzzy controller. In general, fuzzy control systems are extremely simple. Input variables are mapped into the appropriate membership functions, the input pertinence functions, and truth values. The processing stage invokes each appropriate rule and generates a result for each, then combines the results of the rules. The output stage converts the combined result back into a specific control output value using output pertinence functions. Considering this scenario, here is our problem. Given an implicit function, and the vehicle's initial position, how can we make it converge to the curve defined by the implicit function and keep tracking it? In this case, consider three possible initial situations. 1. The robot starts inside the curve. 2. The robot starts outside the curve. 3. The robot starts in the curve. In order to solve this problem, our methodology is based on defining the trajectory by using an implicit function, and then calculates its tangential and normal components in order to get its vector field equation. Our robot will be based on a unicycle vehicle model, which is a non-holonomic vehicle. We then define a closed-loop control system, in which the system's input is given by calculating the position error. The error is the artificial vector field desired configuration on a given time t, minus the kinematic model of the vehicle in that same given time t. This generates our input signal for the fuzzy controller. Finally, the input signal processed by our fuzzy controller maps the input error signals into angular and linear velocities. Those velocities are used as control inputs for our vehicle. Our experiments consists in simulation for trajectory tracking considering three different curves and the three possible initial situations. 1. When the robot starts inside the curve. 2. When the robot starts in the curve. 3. When the robot starts outside the curve. In all experiments the trajectory is represented by a black full line. Here is the simulation results of our first experiment. On our first experiment, figure A shows that both the actuators for linear and angular speed do not present any kind of significant oscillation, and the values for both are completely stable as the vehicle reaches the desired curve and starts to track it. Figure B presents a different result for the actuators when the vehicle starts its trajectory tracking from a point outside the curve. It is possible to see an oscillation as the vehicle starts its movement, since the orientation of the vehicle is initially randomized. A possible interpretation for the initial oscillations can be analyzed as a vehicle's attempt to point towards its objective. Once the vehicle is finally facing its goal, it just moves in its direction, and it is possible to see that the actuators became stabilized and a trajectory is successfully tracked. When it comes to analyzing the actuator's oscillation values, it is possible to see that the oscillation's magnitude are not a problem, since it is a feasible value for a real vehicle. Finally, figure C shows the result of the trajectory tracking task when the vehicle starts at a point that belongs to the curve. As it can be seen, both actuators display a really small oscillation but quickly stabilize on a value in order to keep tracking the desired curve. Those oscillations do not compromise the vehicle task, which is really well performed by the vehicle. Here is the simulation results of our second experiment. In figures A, B, and C, it is possible to see that both actuators oscillate in a significant form. However, the magnitude of those oscillations are not so relevant. Despite the fact that the oscillation's magnitude are not so significant, it is definitely an undesirable result, meaning that the fuzzy controller is capable of performing the desired task, but it is probably not the ideal one when dealing with trajectories containing accentuated curves. Here is the simulation results of our third experiment. Both the actuators continue to present oscillation during the tracking task, as can be seen on figures A, B, and C. This problem occurs mainly when the vehicle approaches the two more sharpened corners in the middle of the curve, even though the oscillations' magnitude are small, which makes the controller's application feasible in a real vehicle. They are not desired. Simulations show that using fuzzy controllers to control vehicles designed to perform trajectory tracking tasks when trajectories are defined by implicit curves is a promising idea. On the bright side, fuzzy controllers are easy to implement and design, which makes it a really interesting approach when dealing with simple and complex systems, since it is only necessary to correctly map the linguistic variables into the system's inputs. However, on our tests, fuzzy controllers designed to control vehicles that perform trajectory tracking tasks did not present good behavior in trajectories that contains accentuated curves.